Okay, so welcome everyone. And today we're going to cover the topic of multiple regression, which is a preview of what you're going to do lots and lots of in Biostat 1 and in probably every one of your Epi and Bios classes starting next semester. So it'll just be a little preview of it for you today. This is covered in Chapter 7 of your textbook. I'm going to start with a review of some of the bivariate methods and then give some description and examples of reading the tables that you will see for multiple regression, along with a little discussion of collinearity and an adjusted R-squared that we use in multiple regression. You'll recall that in regression, we talk about a response variable or an outcome variable, and also predictor variables or the independent variables. And we do this even when causality is unknown for observational data, but this is terminology that describes how you are setting up your regression equation, where your response variable, the one that you're going to consider to be dependent, or the one that is predicted by the independent predictors, is on your y-axis. We covered the case with two categorical variables, and we didn't use regression in this case. We discussed the making of contingency tables, or so-called frequency tables, and the chi-squared test as a way of testing for association between the two categorical variables. And for describing these, there's the frequency tables, also odds ratios and risk ratios. And I'll just note that it is possible also to use logistic regression in this two categorical variable case, a univariate logistic regression, but we don't get into logistic regression in this course, but that will be a large part of your focus in Biostat 1 next semester. So that was two categorical variables. When you have a continuous, yes, question. Sorry, could you speak up a little? So the question is, when you have a multi-level categorical variable like race, ethnicity, is it easier to do a 2x2 table for one race, ethnicity at a time, or what was the alternative you suggested? Okay, so, or for logistic, can you put it all under one variable? So in logistic regression, your response variable must be binary. So you could have like black versus non-black, for example, but you can't have a multi-category response variable. What you can do is, as a predictor, that's no problem. If race, ethnicity is one of your predictors, it's no problem that it's categorical. What goes on inside your software is that it will recode it as several dummy variables, like black versus non-black, white versus non-white, Hawaiian versus non-Hawaiian. But for response variables, it gets kind of complicated. It's in the realm of categorical data analysis that there isn't a simple answer for. There are several approaches for dealing with multi-categorical category response variables, and it depends on what your objectives are. Just as an example, if your objective is simply to predict, to say try to predict race ethnicity based on several other variables, you might fit several logistic regression models, one for each possible value of your outcome. So you fit one model for black versus non-black, another one for white versus non-white, and then you predict the one that has the highest probability from your logistic regression model. But it's a bit of a workaround to the fact that logistic regression itself only works for a binary response. Yeah, there are a lot of different scenarios, but in general, it's hard to give a single answer for what approach you're going to take. In general, I can say it's a lot easier if your categorical variables are all independent. That I can say in general. Thank you for the question. Any other questions? Yeah, this is it's during this review time, and I'll have a bit of time there. Any general statistical questions that have arisen about your project, I'm more than happy to answer them today. In the case with a continuous response and a categorical predictor was what we introduced analysis of variance for, or t-tests if it is just a binary predictor, ANOVA for binary or multi-category predictors. That's a one-way analysis of variance. And for description of this, you could use a box plot or a bar plot. And then finally, last week, or my avatar presented this to you, the linear regression, where you have a continuous response and a continuous predictor. That was linear regression and the R-squared and the coefficient of determination. Multiple regression can incorporate all of these. It's just the general case where you have one response variable and multiple predictors or independent variables. And those independent variables can be any of the types that we've covered. And the response variable can be any of those types as well. Let's start. Let me describe the idea to you with an example. Not a public health example, but one where the interpretation of a model that will fit will be readily interpretable, and the causality is clear. So this is a data set that is available in R that's just the weights of books, and it gives the weights of 15 books. And for each of them, it gives its height, its width, and whether it's a hardcover or a paperback book. And it's a good example for several reasons. We have this volume actually is I think this is still showing the height and wait a minute. Why is it? This is the volume. I'm not sure why the formatting got shifted a little bit here. But so we've got one response variable, weight, and then we have two predictors, the volume, which is the length times the width times the height, and whether it is paperback or softcover. So here's a nice descriptive scatter plot showing the weight of the book on the y-axis and the volume in cubic centimeters on the x-axis, along with the best fit linear regression. So the best fit line is that the weight is 108 grams plus 0.7 times volume in cubic centimeters, and you get an R squared of 0.8 or 80%. So just to review the linear regression stuff, who wants to tell me which of the following is the correct interpretation of this R squared? Or maybe you can tell me first which ones are definitely not correct. Go for it, don't be shy. Make it easy, pick one out that's definitely wrong. And what's that? The last one, the volume underestimates the weight of the book with the highest volume. That's right, that's definitely wrong. It actually overestimates the weight of this one. So that's wrong. Anyone else? Here, maybe I'll make this one a little bigger to, we haven't had a whole lot of questions, so. So how about A, weights of 80% of the books can be predicted accurately using this model? How about a show of thumbs? Give me a thumbs up or a thumbs down. Okay, good, good. Yeah, lots of thumbs down. Yeah, that's just a wrong interpretation of R squared. Nothing to do with, I mean, what would it even mean? Is this book predicted accurately or not? I don't know. There's like, you know, there isn't really a threshold between accurate prediction and not accurate prediction. That's just not what R squared means. How about C, the correlation? So Pearson's correlation is 0.8 squared. Let's see those thumbs. I only see about 20% of people putting in any opinion. One of you thumbs down people want to say why? Uh-huh.
Okay, so capital R squared, but not it's capital R squared. When you square it, they could like the difference between the R squared and why the correlation.
So you're saying the direction is not necessarily the same?
Wait,
Little r can be positive or negative. That's right, the Pearson correlation. What's it going to be in this case, positive or negative? Positive, yeah. Do you remember the relationship between little r and big R? Yeah. Yeah, little r is it's plus or minus the square root of big R squared. So it's not the square of it, it's the square root. So if this had said square root of 0.8, which is going to be something more like 0.9, that would be correct. That would be the correlation. So that leaves us with the right answer, that books that are 10 cubic centimeters over average are expected to weigh 7 grams over average. And for that matter, books that weigh 10 that have 10 cubic centimeters of volume more than any reference point will weigh on average 7 grams more. Doesn't matter that it's the average that it's the reference point. It could be over the minimum or over one particular book. It doesn't matter. So there we go. Good job. here is well, this is the output that you would get in R. It's pretty similar to the one you get in SPSS. Kind of good to get used to reading the tables from different software, because it forces you to think about the parts of them, because they all report the same thing to you more or less. They just have a little bit different formatting. But this is the linear regression fit. So we've got an intercept, we've got volume, which is the slope for volume, which is like we saw on the previous page. So it's 108 plus 0.7 times the volume. And we've got a nice small p-value for volume, showing that we have evidence of a relationship between the volume of the book and a weight, as we would expect. Here's our multiple R squared, 0.80, as I promised, and something called an adjusted R squared, which we're going to get to later in this class. Degrees of freedom, that was the 15 books minus the two things that we fit to it, the slope, or the intercept and the slope. But we had this other variable, right? We had whether it was paperback or hardcover. And it turns out that some of those unexplained residuals on the previous page, like the errors in the prediction, it turns out you can explain it by whether the book is hardcover or softcover. And if we make a slightly nicer scatter plot, where we make the hardcover books into blue squares and the paperbacks into green triangles, you can see that best fit line that was somewhere in the middle here, like, you know, it was somewhere like this. It's over predicting the paperbacks and under predicting the hardcovers on average for most of the books. Note how I like in this figure how hardcovers and paperbacks, they differ by both the shape and the color, because using different colors can help highlight differences in your plot, but sometimes people are going to print it out in black and white, or people have different perceptions of color. Some people are colorblind, so it's always good to use both the shape and the color. Just an aside on presentations, since you're preparing your presentations for next week. It's not good to rely on color alone unless you absolutely have to. So this is starting to motivate multiple regression. You can imagine that we might get a better predictive model here if we were using both book volume and whether it was hardcover or softcover to predict the weight. And that's exactly what we can do with multiple regression. And it turns out that it's really not much harder to do than linear regression. We're not going to get into the mechanics of how you do it, but when you do it, it's really basically as simple as adding another variable to your independence. If you're in SPSS, or using a plus in your model formula if you're in SAS or R. There's more to the interpretation and lots of varieties of models, but at its base, doing what we're doing now and adding another variable to make a simple regression into a multiple regression, it's pretty easy. And interpretation of this table is also not too much of a stretch from what we've already done. So we've got we've still got the intercept term. We've still got a volume, that's a slope. So we find that still, on average, a book that weighs 10 cubic centimeters or has 10 cubic centimeters more volume weighs 7 grams more. But we have a third row here that says color : PB for paperback. And what this is is the correction that we're going to add to the prediction if it's a paperback. Everything else, same. We still have p-values for each of our estimates. That's a p-value against the null hypothesis that the true population value of this estimate is 0. Got your standard errors and t-statistics. You'll notice that this multiple R² and the adjusted R² just went up a whole bunch. It was like 0.80 before, right? And by adding this term, it's now gone up to 0.9275 for the multiple R² and up to 0.915 for the adjusted R². So it looks like this has helped our model as we've expected it to. It means that we're explaining more of the variance with the model compared to the unexplained, or compared to the total variance. So a quick, another quick quiz here for you, and I gave you a hint as to this on the last slide. Based on this regression output, what kind of book is like your reference? Yes. Yes. So we have chosen the hardcover book as the reference category. So what that means is that as we interpret our model, the intercept is going to be the weight of a book that has 0 volume and is of the reference category. So it will be a hardcover book of 0 volume, would be what this intercept means. And then we would add the volume times this coefficient, and we would apply this correction minus 184 if it's not the reference, if it is a paperback book. The correction is added. You go down. So if you're making a prediction, and I'm spoiling my thunder on some later slides, but it'll let us go over those more quickly. But if you're making a prediction of the weight of a book, what you will do is start on row 1. Every single book starts with an estimate of 197.9628. Then we add the volume times 0.718. Then if it's a hardcover, we're done. That's the prediction. If it's a soft cover, we then subtract 184.0473 from that estimate, and that is our prediction. And these tables in a big multiple regression can go on and on. They can have like 20 or 30 rows, but that is the way you make predictions from them. You know, you just go down row by row. For a continuous variable, you just multiply the value of it by its slope. For a binary variable, there will be just one row here for the non-reference category. What if we had another category of books that was, say, magazine? Yep.
Probably have another cover from the magazine.
Yep, that's right. So if we had another type of book that was magazine, there would be another row here that would say cover : magazine, and it would give you another estimate for that. So then if you had a magazine, you would start with the intercept, add the volume times the slope. You would just skip past cover paperback because it's not a paperback, and then you'd go to the line that said cover magazine and add or subtract whatever was there. Probably subtract, assuming that magazines have thinner pages. So the interpretation of them, this is a so-called additive model because you go down here adding. In BIOS 1, you're going to learn about another type. Logistic regression, for example, is a multiplicative model, and you would actually go down here multiplying instead of adding. Or you would add on the log scale and then exponentiate it, so it's the same thing as multiplying if you weren't on the log scale. The point is here, each row in the line adds or subtracts something to your prediction. All right, so which of the below correctly describes the roles of variables in this logistic regression model? So let's start by eliminating some things. What's the response variable here? What's that? Weight, yeah. So let's eliminate C. It's definitely not that. And what are our explanatory variables? Our independent or predictor variables? Yep. Yeah, volume, so we can get rid of, oh, no, that doesn't help us eliminate any of these. What did you say the second one was? Cover type. Yep, there we go. Put a big X through these. Very good. Okay, we've covered how to make predictions. Here it is written down, so you'll have it in, your notes. But again, it's just, this is your equation, your predicted weight. This hat over it just means it's predicted. It's the intercept plus the slope for volume times volume minus 184.05 if cover is paperback. Any questions? Yep. Sorry? Yeah, so the way you would actually do it in logistic regression is you would most likely use log odds coefficients, and you would add them like with this, but then in the end, to predict your probability of either class, you would take the inverse logit, which is going from log odds to probability. And in doing that, you exponentiate. So, so if you have, here if you have cover paperback, I don't know, minus 184 isn't a great example. Let's say it was like 3 or something. If you have two different deviations from the reference category, and each of them has a coefficient of 3, then in this model it would add 6 to your prediction of the weight. Whereas in a logistic regression, those would be odds ratios. And if you have two different variables, each with an odds ratio of 3, then so you have one that is cover paperback and another one that is I don't know whether it's encased in gold or something. And if it is both, you would multiply them. So you would actually have a 9 times greater odds ratio. It matters a lot for things like age in a logistic regression model, in that, someone who is 10 years older compared to 1 year older, you'll be multiplying those odds ratios per year instead of just adding them. Good question. Looking ahead to logistic regression. here is just a nice visualization of this linear model. That regression equation can really be interpreted as two lines, because by subtracting one value for all paperback books, it's equivalent to changing the intercept for paperback books, but not changing the slope. So you can draw it as two separate lines, one for hardcover books and one for paperback books. And those lines are parallel. Here's kind of a, I don't know, an advanced question, I guess, but does anyone know what you would call it if these two lines, if you fit a model where these two lines were not parallel? What would that be called? So the slope is not the same then for paperback and hardcover books. No, not a partial regression. Yeah. It would be an interaction, exactly. It means that the effect of volume depends on whether it's hardcover or soft cover. So those two variables are interacting. I mean, that might happen if in general hardcover books had thicker pages. I don't know, or had pages made of something other than paper. So this is what a fit of one continuous, one categorical variable with no interaction looks like. If we had magazine in here, then we would just add a third level or a third line to it. I'm trying to think of what you're thinking of with partial regression, but I'm not sure. The classifications that I think of are conditional regression and marginal regression. But multiple regression. Yeah, in calculus, there's the idea of partial derivatives, and which is how your response changes as you change only one of the predictors and hold everything else fixed. So it might be related to like the interpretation of the coefficients, that they're partial derivatives with respect to one of your predictor variables. So let's go ahead and interpret these. It's always good when you have your table to put these coefficients into words, so you could explain to someone what they mean. So the intercept here is what a hardcover book with no volume is expected on average to weigh. I don't know, the intercept, it doesn't really make sense to have a zero volume book. Maybe though the volume is just the volume of the pages and not the cover. So maybe it's the intercept is the weight of the cover of a hardcover. I don't know. The slope of the volume, that is all else held constant, as in a partial derivative. Books that are 1 cubic centimeter greater volume tend to weigh 0.72 grams more. And the slope of the cover means that all else held constant, so you're holding the volume constant. Paperback books tend to weigh 184 grams less than hardcover books. I'm gonna skip over this. I think you've got the hang of how to make predictions for this. You start with the intercept. I guess we can go through this quickly. a paperback book that weighs 600 cubic centimeters. What is the predicted weight? So we start with the slope, 197, which allows us to eliminate this. It weighs 600 cubic centimeters, so has to be one of these. I'm going to eliminate D. And then it's a paperback, so someone tell me which of A and C is correct. A, yep. Nice big hockey stick there. Multiple regression is fun, right? All right, so let's move on to another public health example of modeling poverty. And I guess I got this cut off a little bit, including cutting off the source. But this is a data set that is common in, it has some properties that are common to a lot of public use data sets that I've worked with that are collected and provided by the federal government and also by New York City. But what they often do is they do not provide you with individual data on individuals, but they'll provide you with data on areas, on census tracts, or zip codes, or counties. And so this data set is like that in that it has neighborhoods, and for each neighborhood, it provides the percent of residents living below the poverty line, along with several predictor variables, which are the percent of residents in metropolitan areas. So this is a measure of how urban the area is. The percent of residents self-reported as white, percent of residents who graduated high school, and the percent of households with a female, with only a female head of the household. And if anyone is interested too, I will dig out the, I did all of this with R code. I know there's at least one person learning R already in the course, but I can dig this out. This is a kind of a useful descriptive statistics approach graphically that you can do for multiple regression, which is just making scatter plots for all pairs of variables. I call them the pairs plot. So I'm plotting the response variable, this poverty, and then all of the other predictor variables. And the way you read this is that if you go to the right of something, that is what's on the y-axis, and if you go above something, that's what's on the x-axis. So for this particular plot, this is poverty on the y-axis and the percent of metropolitan residents on the x-axis. And you can see that just looking visually by eye, there isn't a great association, but it's also showing us the Pearson correlation in the corresponding mirror image. And you see the Pearson correlation there is minus 0.2. In fact, we can quickly look across and see where are there any strong associations. There isn't really enough variation in percent white to be able to say whether there's a strong association, but there is a pretty good association with the percent of high school grads. There's definitely a negative correlation, minus 0.75. And there's also a pretty good correlation with the percentage of female heads of household that's positive. There's a correlation of 0.53. So we've got 4 potential predictors here, and we can immediately see that some of them are stronger than others. And you can also look at at other pairs. For example, high school percentage of high school grads and female heads of household, we've got a pretty good negative correlation. And I'm going to define this later, but that's what we call collinearity among our predictors. It means there's a pretty strong relationship between high school graduation rates and rates of female heads of household, where there are higher percentages of female heads of household, there are lower high school graduation rates, which is kind of interesting, just in that we had this negative relationship between poverty and high school graduation rate, and this positive relationship between poverty and female heads of household. So I don't know, I need to scratch my head for a minute. Any ideas about how that might happen? Yep. Sorry, did I explain what? Mm-hmm. I'm having a hard time hearing. Which spot? Oh, okay, one spot. So actually, I think one spot, one dot here is a state. This is statewide data. So for each state in the District of Columbia, one dot tells you what the poverty level is. So this one up near the top would be something near 15%. And it would tell you in this particular plot the percentage of residents that are in metropolitan areas. And for this particular point, it's a little below 50%. And it's a different, so if you go along this first row, the y-axis is the same. It's the percentage of households below the poverty line, but the x is different for each one. Here, it's the fraction of residents self-reporting as white. Here, it's the percentage of people who have completed high school. And here it's the fraction, or the percent of households with a female head of house only. Yeah, or 51. Yeah. So we have we have less poverty with more high school graduation, and we have more poverty with a higher percentage of female-only heads of house. And we have a negative relationship between them. So as you have a higher proportion of, oh, yep. Yeah, I did. Good question. I'm not sure off the top of my head, but would that affect your explanation? So it's more common for older women not to be in a single family household. And those older households may also have a higher income. That is a possibility. It's getting into a causal explanation of it, which I guess I was still thinking at the stage of it might actually be impossible to define the effects of high school graduation and female heads of household. But you're exactly right that it getting into that explaining of these things gets out of the realm of statistics and into the realm of, like, you know, understanding sociology and some of the factors affecting poverty, and sort of a deeper understanding than we can get from this data set. Do you have a? Yeah, so teen pregnancy is another is another good possibility. Yeah. The more educated women are likely to be married, maybe because they're older also, and we have less poverty. Maybe, I don't know. But the thing that all of these explanations are getting at is that there is an association between the rates of high school graduation and the percents of female heads of household. And the true explanation of poverty might be one or the other of those things, or it might be something else that is affecting both of those things. And that's really what I wanted to get at. And when you have, this is called collinearity, and when it's present in a data set, you can't disentangle that just based on the data. You have to undertake an exercise like what we're doing here, and then find additional data and test these alternative hypotheses, and try to find a way to establish what the true causal relation is. So thank you. Those are help a lot with the lecture, having some input like that. Here's a simple linear regression just with the poverty and the percents female heads of house, and you see this positive slope with the an estimate of 0.69 and an R² of 0.28. So you'll recall maybe that that the relationship between slope and Pearson correlation, it's just the scaling. The Pearson correlation would be the slope if you scaled all of your variables to unit standard deviation, and R² is the square of that. But in fact, there are several ways to calculate R². One is to square the correlation coefficient between x and y. You can do that in a simple linear regression, right? You can't do that in a multiple regression because you have multiple x variables. But for a linear regression like that, you can do this. You can square the correlation between your actual response variable and your predicted response variables. That's going to work in a multiple regression. You can do that. Or based on the definition, that's your explained variability in y divided by your total variability in y. And that final one, you can get those explained and total variability from an ANOVA table. How are we doing for time? I want to wrap up pretty quickly here. So I think I'm going to skim over this, and just to say you can create an analysis of variance table not only for actual ANOVA with a categorical X variable, but also for linear regressions. ANOVA tables are useful for any kind of regression. It's just an analysis of your variance terms. So it will tell you useful things like your total variance, the amount of variance of your residuals, and the variance of components of your model. And in this case, you can get your explained variability just by your variance of your female heads of house term divided by your total variance. So it's kind of nice to show that you understand your analysis of variance tables by being able to recreate the R-squared that the software is also going to give to you. Why bother with 3 ways? That first way is only going to work for a linear regression. The second way is good for any kind of regression. And the third was a definition. So the second and the third, you can choose between either of those for a multiple regression. In multiple regression, we've got the R-squared. We've also got this so-called adjusted R-squared that I've mentioned and given one example of. Let's see. Okay, I showed you the ANOVA table for just one variable. That's this first thing. Below, I'm showing you another variance table for adding a second term to the model, which is the variable called white, the fraction of people who are self-reported white. And it just adds another row to this analysis of variance table. You see that the variance explained by this variable is quite a bit less than the fraction of female heads of house. This corresponds to what we saw in those scatter plots. We saw not a very strong relationship between the percent white variable and a stronger association with female heads of household. But you can just add these variance terms. So here our explained variability is 132 plus 8.21, and the total variance term is the same as it was before. So what's going to happen is you add more variables to the model and keep adding more rows to this and keep on calculating R-squared in this way. What's going to happen to R-squared if we add another row to this table, another variable? Well, we're adding to the numerator here. We're adding to the explained variability. It goes up. Yeah, every time you add a variable in a multiple regression model, R-squared goes up. Yes? Does it matter if what? R-squared can't be negative, it's just positive. So if you add a good explanatory variable, it will explain more variance and it will cause a large increase in R-squared. If you add a bad variable that doesn't explain very much of the total variance, it'll only add a little bit to R-squared. But it will always add something because you're going to fit an optimal coefficient for it for this data set. Yes? Yeah, good question. Is there a cutoff where that's a good R squared? There are traditions in certain fields. In general, the answer is no. It's a continuous thing. A little more is always a little better. A lot more is a lot better. I've heard that in astronomy, if you find a correlation between something and like the distance of stars, and you get a correlation of 0.05, that's really something great. In some other areas, you expect quite a high correlation, but no, there isn't an answer. I've had my own feeling is it depends on why you're fitting the model. There are some situations where just finding that there is any non-zero relationship at all is something important. It shows that there is some relationship, and so a small association is okay. And you imagine that there's a lot of noise, or there's a lot of intermediate factors between the cause and effect there. In other ones where you want, like, you have two different lab tests and they're supposed to be telling you the same thing, or they're replicate measurements, you expect like 0.99. So yeah, context dependent. But as long as you understand that definition of it, that it's your explained variance divided by your total variance, then you'll be able to decide whether you think it's good or not. Any other? Yes. About an interaction. When you do what? The R squared goes down, or the adjusted R squared? Right, so we're going to get to adjusted R squared. That's why we use it. I'm going to do a bit of glossing over here. We've talked about collinearity. It's when you have correlation between your predictor variables. Collinearity complicates things because you can't tell which one is the predictor when they both. An example with the book thing would have been if we used both height and width as a predictor. They probably would have been collinear, because as the height of a book increases, so does the width. It would have been hard to make a predictor. In that case, calculating the volume from it was a good solution to collinearity, but there aren't always good solutions to it. When you have highly collinear variables, I will often just select one and say this is a proxy for some other variable as well, because you have bad behavior of your regression with highly collinear variables. You can take an average. You can do, not yet, but eventually you can do principal components analysis to find one variable that represents several collinear variables. There are various strategies, but the important thing for you to recognize at this point is when you have collinear variables, and you can figure that out by doing pairwise scatter plots, by doing box plots, by doing anything that just by pairs of variables gives you an idea of how strong an association there is between them. You can do chi-squared tests, but the point is just to be aware of collinear variables in your data set. So R squared versus adjusted R squared. The problem with R squared is, as I mentioned, that anytime you add a variable to the model, it will always increase R squared, even if it's not a good variable. If you add interaction terms. Anytime you increase the complexity of your model, you're going to increase R². You're going to add a little bit more ability to predict the response variable, which is where the adjusted R² comes in. It's a correction for the complexity of the model. And it's corrected in a way that in a multiple linear regression, if you add variables that have no association to the outcome, it won't increase. It'll just stay the same or go down. Here's the formula. You could use it if you want, or you can just read it off of the software. But I just want to point out to it that this part on the left is the same as the R². The difference is just this correction factor where P is the number of predictors. So, as your number of predictors increases, then this fraction here on the right gets, let's see, it gets smaller, or sorry, no, it gets, you're subtracting, so the numerator here gets smaller, this gets bigger. If your number of predictors is 0, it's the same as your regular R². If your number of predictors is equal to n minus 1, you should be able to fit perfectly to your data points. Then your adjusted R² is just going to be 0. So a few properties, it's always smaller than R². It penalizes you for your number of predictors. So if your sum of squares of error doesn't go up quickly enough, then it will result in a reduction in your adjusted R². And by the way, the smaller n is, the greater the penalty is for each additional predictor. If you have a very large sample size, then the penalty for adding your first few predictors is very small, but it gets subsequently larger for more predictors in the model. And P here includes also interaction terms and other just rows in your coefficients table or your analysis of variance table. And the R adjusted you can use to choose models. So if you add an interaction term and you see your adjusted R² goes down, that's a reason not to choose your more complex model. Let's not do a manual calculation, but you've got it in your notes. And wrap up. So multiple linear regressions, an additive model. And when you get to logistic regression, you're going to remember that it's a multiplicative model, and keep those straight in your mind. When you take BIOS 2 with me again in the fall, that'll be, I'll make sure to make that very clear. We'll do some other different types of models as well, and every one of them I'll think about whether it is an additive or a multiplicative model. Colinearity is when you have correlation between your predictor variables. As I mentioned, you can identify it by making plots, by doing pairwise tests like correlation, chi-squared tests. You can also notice it in your regression table from very large standard errors of any of your coefficients. It causes large standard errors because it can't determine which of those variables is responsible for an association. So if you have one variable in your model and you add another variable and see that the standard error goes way up, that's a sign of colinearity. And adjusted R² is a good measure of model fit for multiple regressions. This is just kind of a little take-home cheat sheet for you. Summary of statistical methods that we've covered in the first and the third columns, and also some that we didn't cover in this class, which are non-parametric alternatives. So when you have a small sample size and can't make the assumption of normality, or find that there is a gross departure from normality, you can choose these tests as alternatives to ones that we've learned in this class. Finally, you should have all received some reminders and requests from the school to fill out teaching evaluation forms. And I didn't take the time out of class to do it, but I would like to implore you to please go ahead and fill those out, especially if you like the class. But no, everyone should fill those out. They are important especially for junior faculty, but for all of your professors, it is an important part of their evaluations for promotion and tenure, and for the assignment of future classes, for everything. So they really are taken seriously. So please do go ahead and fill them out. And finally, thank you for all of your participation and asking questions and answering my call-outs for questions. It certainly makes the class fun to teach. It's been a fun class, and boy, a great turnout today for our final class. Are there any other questions before I will stop the? I better make sure that there aren't questions from online. Nope. And as soon as there are no more questions, we're going to take a few minutes break. We'll let the people who are going to present their posters today go ahead and get set up. And then we'll come back and do those. All right. Thank you.